Have you ever wondered why we feel colder when we swim in a lake versus when we walk by it on the shore? Now, you might think that this is because the water in the lake is colder than the air surrounding it, but the two are essentially at the same temperature. And the real reason we feel colder in the lake is because our bodies lose heat more quickly to water than to air. Now, let us change gears for a moment and imagine a heated surface underwater, like when you're boiling water to cook pasta. We all see bubbles form at the bottom surface and rise up, right? Now, if we could get this bottom surface really hot, all these bubbles forming down here would eventually cover the entire bottom surface, such that it is only surrounded by vapor and water does not reach down there anymore. Now, remember how our bodies lose heat less quickly to air than to water? The same thing applies to this surface. Because it is surrounded by vapor now, it cannot lose heat as quickly, and the surface temperature begins to rise very sharply, and eventually the surface melts. This is known as dry out in boiling and is marked by sharp jumps in the surface temperature. Now, thankfully, you cannot actually see dry out happen on a stovetop because it cannot reach temperatures high enough. But dry out is a big problem in power plant boilers and cooling of supercomputing chips, where boiling is used because it is one of the most efficient methods of transferring heat. As you can imagine, dry out in such cases can cause boilers and chips to burn out, which is unacceptable. And my research is investigating how we can prevent this from happening. In our experiments, we use nanofabrication techniques to deposit microscale temperature sensors like these on such boiling surfaces, and we then progressively bring these surfaces to dry out as we measure temperature fluctuations. We then look for certain patterns in the way these fluctuations behave, which can tell us something about an impending dry out. And the good news is that these fluctuations are actually fractals. Now, very briefly, fractals are these mind-blowing patterns like the snowflake, where when you zoom into a fractal, you see the pattern repeat itself over and over again. And as you can see here, the same thing is true for these fluctuations. My research is trying to understand the origins of fractals in boiling, but our ultimate goal is to use the fractals in these temperature fluctuations as a signal to predict when a surface is close to dry out, so that we can then take control measures to prevent the surface from melting. This is a lot like using heartbeats to monitor the status of the heart. Only in this case, we are using temperature fluctuations to monitor the status of the surface. And to recap, the outcomes of this research can be used to improve boiling performance and safety margins in power plants, supercomputing chips, or anywhere else where dry out is a problem. And this is why I feel so excited about boiling water more effectively. Thank you.